Hello, I'm Mike McCulloch. Today I'd like to talk to you about lifters, which are a very interesting phenomenon, which were first identified by T.T. Brown about 100 years ago and patented, and they have developed a bit since then. And these days, several people have experimented with them, and they look a bit like this. So you can see here there's a triangular shape, but it could also be square, and it can be linear as well. But they have a aluminium foil skirt, if you like, below, and then they usually have a balsa wood stick sticking up in three places and connected to a wire, which is a bit like an aerial above the foil. And the foil is usually grounded, and the wire is usually set to either positive or negative. It works both ways. And it's what is thought happens is that ions form near the wire because the electric field is so strong there, because the wire is quite thin, so the gradient is strong. So ions form, and if they happen to be positive, they migrate towards the foil, which is grounded, and it's therefore more negative. And if it's negative, again, if the ions are negative, they again are attracted towards the grounded foil. And so the recoil on the system of this ion wind pushing down forces it up. So that's all well and good, and this ion drift explanation has been accepted for decades. But there was a very interesting paper published in 2014 by Einat and Calderon, who looked at this from a more rigorous standpoint. They did various tests and changed the structure of the lifter to see what happened. And the first interesting thing they noticed was that if they had more than one wire, if they added more wires, there was less thrust. So this is not consistent with the ion drift explanation, because if you have more wires, you should have more ions able to be produced, because there's more surface area of wire up there. But in fact, there was less thrust, which isn't consistent with that. But this is more consistent with quantized inertia, because the explanation in quantized inertia would be that yes, ions are forming at the wire as per normal physics, and yes, have been attracted by the foil, rather as in the capacitor experiments of Becker and Batt and others that have produced thrust. The ions are accelerated rapidly towards the foil, but they also, because the acceleration is so rapid, the Unruh waves that these electrons see is short enough to interact with the structure, and more Unruh waves are damped below by the foil because there's more area of foil, and fewer Unruh waves are damped above by the wire because there's much less area of wire because they're thin. So there's a supervoid in the vacuum below, so the ions are pulled more than expected downwards. So this would mean that if you add more wires at the top, you'll start to damp Unruh waves there as well. So the gradient in the Unruh vacuum would be reduced, and so the thrust would decrease, as was seen. Also, Einat and Calderon saw that if they added a load of foils below, they increased the thrust. Now, in the ion drift explanation, that shouldn't increase the thrust, because the number of ions depends on the number of should, in the theory, depend on the number of wires, except it doesn't, not on the number of foils you have. But Einat and Calderon found that the more foils they had, the more thrust they had, which again is consistent with QI, because it means more Unruh waves are damped below, the ions are pulled down more than expected, and you get more thrust up. They also showed that the thrust was very proportional to the area of the foil, which is very consistent with quantized inertia. More generally, the ion drift theory suggests that the force should look something like this. So the force should be the current times the distance between the wire and the foil divided by a constant. But in fact, Einat and Calderon showed that it was actually not the case. The force is inversely proportional to the distance between the wire and the foil. But in quantized inertia, we have a formula more like this. So the force is the current times the area divided by the distance squared. So this is more consistent with what we're seeing. So can we calculate the force from quantized inertia? Well, I published a paper doing this for a capacitor similar to one of these, shown here. And the force is given by F is PQ over C. The quality factor, now this assumes that these underwaves waves are resonating within the cavity formed by the foil and the wire. You can think of it as a closed cavity. And Q is equal to 2 pi F E over P, where F is the resonant frequency, E is the comes from the capacitance, that's the energy stored in the capacitor regarding this as a capacitor. So it's half CV squared, where C is capacitance and V is voltage, divided by P, which cancels with the V and the P above in the equation. So we have this result for the force, which for a typical lifter gives a force of about 140 millinewtons, whereas the force that they know they must exceed to lift off most of these typical ones is on the order of 40 millinewtons, or it depends on the weight, of course, but it's around about that size. So quantized inertia is perfectly capable of predicting these forces, and it's more consistent with the actual data in this Einat and Calderon paper. The great thing about this is that the capacitor test of quantized inertial thrust is quite difficult to reproduce. If it's true that these lifters do in fact follow QI rules like this, then it's an experiment that many more people could do. It's much easier to do, and it would be perhaps a better way to prove it. In fact, it may already be doing that with these anomalies, which have discredited the ion drift theory. So, okay, so I hope you've enjoyed this short, and I look forward to speaking to you again next time. Goodbye.